Hello everyone. Today we will introduce support vector classifiers. It is one of the most popular machine learning methods. Our topic for today starts from maximum margin classifier, then move on to the support vector classifiers. So far, we have covered quite a number of machine learning models including decision trees and random forest, which are well-used methods in machine learning. We learned the theory behind the methods and also their work in practice. You can see those videos using the link above. Let us start. Support vector classifier is a method developed for classification in 1990s. The method was initially used in the computer science community. The original idea is based on maximal margin classifier, which we will cover in a moment. Extending the maximal margin classifier brings us support vector classifiers, which is an elegant and simple approach. The method attracts many scientists so that it is further extended and ended up with the support vector machines. We will first look at what maximal margin classifier is. Maximal margin classifier has an intuitive idea. It sees the data points as points in the p-dimensional space. Further, the method says that we can make classification by finding a hyperplane in the p-dimensional space. Okay, but what is a hyperplane? Hyperplane is a flat affine subspace of dimension p-1, assuming we are in a p-dimensional space. Let us have an example of 3 dimensions. In this case, a hyperplane can be formulated as beta 0 plus beta 1 times x1 plus beta 2 times x2 equal to 0. Here, betas are the parameters. Note that if the equality holds, our data that is shown by x is on the hyperplane. However, if it is not equality, then it means our data falls into one of the sides of the hyperplane. Now, as we learn what a hyperplane is, we can make use of it for our purposes. And remember that our purpose is to make a classification, and we can find the hyperplane that divides our data into 2 classes. This means that we will find the hyperplane such that whenever we try the formula with our data points, we will never get 0. This is called a separating hyperplane, which classifies our data points into -1 or 1. For the method of maximal margin classifier, we are looking for the best separating hyperplane which maximizes the distance to the classes presented on each side. Let's have a look at the formulation of the maximal margin classifier. We are trying to maximize M, that is the margin subject to constraints. The constraints are the summation of beta squares equal to 1 and yi times beta 0 plus beta 1 x1 I plus beta 2 xi2 plus it continues till beta p xip. And this should be greater than or equal to m for each I in our data. The second constraint guarantees that each data point will be classified correctly. This model has an assumption that the data can be divided by a hyperplane. That is, this method does not work with the datasets that are not separable. To deal with non-separability, we focus on support vector classifiers. As we are looking for the best separating hyperplane, we are heavily depending on the dataset. When we use maximal margin classifier, changing a single data point would cause a completely different separating hyperplane. We are looking for a method that is more robust of this kind of changes over the data. Support vector classifiers are used for this aim. It provides more robust solutions for the observations and better classification of most of the training observations. The method is sometimes called soft margin classifier since it allows some of the observations can be predicted false. By this way, it can deal with the non-separable datasets. Let's have a look at the formulation of the support vector classifier. The aim is the same. We are trying to maximize the margin between 2 classes. However, this time we have these different constraints. The constraints are the summation of beta squares equal to 1 and yi times beta 0 plus beta 1 xi1 plus beta 2 xi2 plus till beta p xip greater than or equal to m times 1 minus epsilon I for each I in our data. We have also additional constraints that are each epsilon I should be greater than or equal to 0 and summation of epsilon i's less than or equal to c. Epsilon is the error measure and it is positive when the classifier classifies incorrectly. C is the non-negative parameter of the method and it can be seen as a budget for making incorrect predictions. As seen in the formulation, if we have C equal to 0, the method becomes maximal margin classifier. Let us have a close look at the insights derived from the formulation. First is about epsilons. Each epsilon shows the location of the observation relative to the hyperplane found at the end of solving the formulation. If epsilon I equal to 0, it means that the hyperplane classifies the observation correctly. If it is greater than 0, it means that the method classifies the observation incorrectly so that the budget is used. As said earlier, whenever the budget C equal to 0, we obtain maximal margin classifier. And also as expected, when we increase the budget for making mistakes, our model becomes more tolerant for the incorrect predictions. Today, we covered maximal margin classifier and support vector classifiers. We formulate their mathematical problems. Lastly, we briefly discussed the insights of the mathematical formulation. We would like to hear what you think about our contents. Thank you for watching our videos. Please do not forget to hit the subscribe button. By doing so, you're really helping us to grow. You can always ask questions by leaving a comment below and we will be happy to answer it. In our next video, we will cover the extended version of these methods, which is support vector machines. See you in the next videos. Bye bye.